So using seismic waves, we've been able to differentiate Earth into the layers of the crust, the mantle, and the core. We know that the crust is made out of different types of rock because this is where we live. This is where we are able to observe. So the oceanic crust, the crust that is beneath the oceans that makes up the ocean floor, is approximately 5 to 12 kilometers thick with an average density of about 3 grams per cubic centimeter. It's mainly made up of basalt on the surface, which is a mafic rock, aphanitic, meaning that the crystals are very, very small because it cooled extrusively on the surface of the Earth. So basalt's on the surface of the oceanic crust. Gabbro is beneath the basalt in the oceanic crust. It's also mafic, so it has the same composition of basalt overall, but it's phaneritic, meaning you can see those large crystals because it cooled slowly inside of Earth. So it's an intrusive rock. So we have the dense oceanic crust with basalt on top, gabbro on bottom in that crust. Now the continents are much, much thicker. That crust is thicker. It's about 30 kilometers thick, but they are less dense than their oceanic counterpart, averaging only about 2.7 grams per cubic centimeter. This allows them to float higher on the dense mantle. And when I say float, I don't mean like float on a liquid, because remember the mantle is a solid, but it flows plastically. So you can kind of think of the crust as floating on the mantle. Right. So granted, it's felsic, it's light in color, it's phaneritic, meaning that we can see those crystals, which also means that it cools intrusively. So the heart of the continents is made up mostly of granite. So once again, we have a thin oceanic crust next to thick continental crust. Now, beneath the crust is the mantle. Okay? Now, the upper mantle behaves very similarly to the crust. And by that, I mean that it's more brittle, right? So the crust is brittle. Anytime stress is applied to it, it's likely to break and crack. The upper mantle is very similar, right? When any stress is applied to it, it's likely to break, likely to crack. We call it rigid. So that means that the crust and the upper mantle, even though they're made out of different compositions, behave very similarly in the way that they move, in the way that they flow. We term the crust and upper mantle the lithosphere. The lithosphere, it's rigid, it fractures under pressure, it's composed of the crust and upper mantle. This is separated from the asthenosphere below it. The asthenosphere is the mantle below the lithosphere that does tend to flow, behaves more fluidly, deforms fluidly. Okay? Now, the reason we separate these two layers out, right? So remember, we can separate the Earth into layers based on composition, the crust, mantle, and core, or we can separate the Earth based on how that material flows, the lithosphere and the asthenosphere. The reason we separate out the lithosphere and the asthenosphere is because this is what allows for plate tectonics to exist, right? That rigid lithosphere is what makes up the rigid tectonic plates that glide on top of the more fluid asthenosphere beneath it. Okay? Now, as with many scientific breakthroughs, plate tectonics was not, it took a long time to conceptualize, right? There needed to be a lot of supporting data before the scientific theory was widely accepted. It was not widely accepted until the 1960s and not taught widely in school until the 1970s.